Welcome to another deep dive. Today we're tackling a really tricky puzzle in cause and effect. What happens when the things influencing outcomes are hidden? Unobserved, sneaky variables.
Yeah, it's a fundamental problem.
We'll explore how experts try to untangle this, how they identify true causal links from observational data, even when, well, you don't have all the pieces.
Right. And our guide for this is Chapter 12, Unobserved Confounders, Instrumental Variables, and Proxy Controls from Applied Causal Inference powered by ML and AI.
And the authors are a real powerhouse team.
Yeah.
Victor Chernosikov, Christian Hansen, Nathan Callis, Martin Spindler, and Vasilis Serkanis. Quite the lineup.
Definitely. So our mission today is basically to walk you through how these pretty sophisticated tools help us get past just seeing things are related.
Right, beyond correlation.
Exactly. To understanding what causes what, it's about seeing that hidden structure, even if you can't directly observe every single part of it.
Okay, let's unpack this core challenge then. Causal inference, figuring out if, say, D causes Y, not just if they move together. And the big hurdle, these unobserved confounders.
Precisely. So imagine there's this hidden thing, let's call it A.
Okay.
And A influences both your potential cause, D, and your outcome, Y.
So it makes it look like D is causing Y directly.
But it might just be A pulling the strings on both sides. It's a classic issue. There's that great quote, kind of a riff on Tolstoy.
Oh yeah, the Anna Karenina one.
That's the one. All happy statisticians are happy in their own way, but all the unhappy ones, they all do causal inference with observational data.
Oh, it really nails the frustration, doesn't it? Working with messy, real-world data.
It absolutely does.
So let's make this concrete. Imagine you want to know if more education, that's our D, actually causes higher wages, or Y.
Okay. Simple model. Education leads to wages. Arrow from D to Y.
Straightforward enough.
What if there's something like, say, latent, our hidden A? You can't really measure it perfectly.
Right, like inherent talent or drive.
Exactly. And what if that ability influences both how much education someone gets and how much they earn later?
Okay. So ability affects education and ability affects wages.
Yep. And here's the kicker. Without being able to see or measure ability, those two stories, education directly causing wages versus ability causing both, they look identical in the data.
They're statistically indistinguishable.
Precisely. The correlation between education and wages is there, but you can't tell if it's true causation from D to Y or just this shared cause, A, creating the link.
So basically we're stuck if we don't do something more.
Unless we make more assumptions or, get clever.
Thankfully, the chapter lays out three main paths forward.
Right. Sensitivity analysis, instrumental variables, IVs, and proxy controls.
Okay, let's start with sensitivity analysis. What's the core idea there?
Well, if you can't see the confounder, maybe you can at least put some bounds on how strong its effect could be.
So estimate its potential impact.
Kind of. Sensitivity analysis helps you figure out how robust your conclusions are, even knowing there might be this hidden factor, A, messing things up.
How does that work conceptually?
Okay, imagine you have your model cause D, outcome Y, and you've already controlled for everything you can see. Let's call that X.
Right, the observable background stuff.
But there's still this potential omitted confounder bias from the hidden A. Sensitivity analysis tries to quantify this bias. It uses concepts related to partial R squared.
Partial R squared. What does that tell us?
Think of it like this. How much of the variation, the scatter, in your cause D and your outcome Y, could this unseen confounder A possibly explain, even after accounting for X? It puts a number on the potential strength of the hidden variable.
Okay, that makes sense. It's like asking, how bad could this hidden thing be? Got a real-world example.
Sure. The chapter mentions the Darfur Wars study. Researchers wanted to know the effect of experiencing direct war violence. That's D on people's attitudes towards peace. That's why. They used survey data from refugees.
Okay, and the challenge there is obvious, right? Experiencing violence isn't random.
Exactly. There could be all sorts of unobserved things, maybe pre-existing beliefs, personality traits influencing both exposure to violence and peace attitudes. That's your A.
So what did they do?
They controlled for observed demographics, X. But the clever part was benchmarking. They looked at how much variation their observed controls, X, could explain. Let's say, just hypothetically, X explained 13% of the variation in peace attitudes and maybe 1% in violence exposure.
Okay.
They might then assume that any unobserved confounder, A, is probably no stronger than those observed factors. It's a reasonable starting point.
That is clever. You use what you can see to put a plausible limit on what you can't see.
Precisely. So they plug these benchmark values into a formula and estimate the potential bias. In their case, it came out to something like 0.0236.
And how do you use that number?
You can visualize it with a sensitivity contour plot. Think of it as drawing a boundary on a graph. The graph shows different combinations of how strongly A might affect D and Y. Any combination below the line or contour means the bias would be smaller than their estimated 0.0236.
So it shows you how strong the confounding would need to be to actually overturn your initial finding.
Exactly. For instance, you might see that if you believe the hidden confounder explains, say, 5% of the variation in violence exposure, D, it would have to have almost no effect on peace attitudes, Y, for the bias to stay small. It gives you a feel for the result's robustness.
That's really useful. It acknowledges the uncertainty. But what if we want to do more than just bound the bias? Can we actually isolate the true effect?
That's where the next technique comes in. Instrumental variables, or IVs.
Okay, IVs. What's the big idea here?
The big idea is, when you've got these unobserved confounders, you look for another variable, let's call it Z.
A new player, Z.
Right, and Z has to satisfy some specific conditions. It needs to influence your treatment, D.
Okay, so Z affects D.
But it should only affect your outcome, Y, through its effect on D. It can't have a direct path to Y itself.
Ah, okay, only indirect influence via D.
And crucially, Z must be independent of the unobserved confounder, A. It can't be mixed up with that hidden factor.
So Z is like clean leverage on D.
You got it. It creates what's called quasi-experimental variation. It's like finding a little natural experiment hidden in your observational data.
That sounds incredibly powerful. And this isn't a new idea, right?
Not at all. Philip Wright introduced it way back in 1928, a real pioneer. He even suggested using things like weather conditions as instruments for supply and demand. His work was foundational for causal diagrams.
The weather. Wow. Okay, back to our education example. Education D, wages, Y, hidden ability A. How does an instrument Z help?
So we need a Z that affects education but doesn't directly affect wages except through education and isn't related to ability.
What kind of things have researchers used as Z for schooling?
Oh, some classics are things like distance to the nearest college.
Okay, closer means more likely to go, maybe?
Right. And distance itself probably doesn't affect your wages decades later except via the education you got. Or compulsory schooling laws, changes in laws forcing kids to stay in school longer.
Ah, that's like an external shock to schooling levels.
Exactly. Or even things like local unemployment rates when someone was, say, 17, that might push them towards more schooling but isn't directly tied to their wages at 30, independent of that scoring decision.
Okay, so you find this Z. How does it actually let you estimate the effect of D on Y? The alpha.
Well, after you statistically control for the other observed factors, X, it often boils down to a surprisingly simple ratio, at least in linear models.
A ratio.
Yeah, you basically look at how much the instrument Z affects the outcome Y and divide that by how much the instrument Z affects the treatment D. So cov Y, Z, over cov D's, roughly speaking.
Wow.
As long as Z actually does affect D, that's the relevance condition, this ratio can identify your causal effect, alpha.
That's elegant.
And modern methods like double machine learning help estimate this very robustly.
And this IV logic applies elsewhere too. You mentioned supply and demand.
Absolutely. Think about estimating price elasticity. Y is demand, D is price. Your unobserved confounder A could be shifting demand in ways you don't see.
Yep.
Your instrument Z could be a supply shifter, like maybe a frost hits Florida orange groves.
Yeah.
That affects supply, which affects the price D of orange juice, but the frost itself doesn't directly change how much people want orange juice at a given price Y.
Got it. Same logic, different context. So Z, dy, and Z is clean.
Mathematically, it's very similar.
Now, does this work if the relationships aren't simple straight lines? Nonlinear models?
It gets more complicated, but yes, IV can still often identify an average marginal effect, but there are more assumptions involved.
What?
Often, you need the unobserved confounder A to affect the outcome Y in a relatively simple way, like additively. Or you need the instrument's effect on the treatment, sometimes called compliance, to be the same for everyone, not varying with A or X. If you have heterogeneity in both the treatment effect and compliance linked to A, the simple IV ratio might not give you the average effect you want.
Okay, so more complexity means more potential pitfalls.
Right. But there are specific nonlinear IV models. One important one is the late model local average treatment effect.
Late. What's that focus on?
This is often used when you have a binary treatment, like did you participate in a job training program? Yes, no. And a binary instrument where you offered the program, yes, no.
Common scenario.
Late doesn't give you the average effect for everyone. It gives you the effect specifically for the compliers.
Compliers.
Yeah, those are the people who actually participate if and only if they're offered. Their treatment status D changes when the instrument Z changes.
Ah, so it isolates the effect just for the subgroup whose behavior the instrument actually influenced.
Exactly. If Z is the offer, D is participation, Y is earnings. Hidden ability A might affect both participation and earnings. Late is identified again by a ratio. The effect of the offer, Z, on earnings, Y, divided by the effect of the offer, Z, on participation, D. It zeroes in on the causal effect for those compliers.
That's a really useful distinction. Not the effect on everyone, but on those moved by the instrument. Any other advanced IV models mentioned?
They briefly touch on the IV quantile model. Instead of just the average effect, this aims to see how the treatment affects different parts of the outcome distribution, like the effect on median earnings or the 90th percentile. Much more advanced, though.
Okay, so IVs are powerful, but need that special Z's variable. What if you don't have a good Z, but you do have some, well, imperfect clues about the hidden confounder A?
That brings us perfectly to the third strategy, proxy controls.
Proxy controls, so using stand-ins for the hidden variable.
Kind of. Imagine you don't have a perfect measure of latent ability, A, but you have two imperfect ones, maybe an SAT score, S, and an ACT score.
Okay, two different test scores, both trying to measure ability, but neither perfectly.
Right. Now, just throwing S and Q into your regression model as controls doesn't fully solve the problem.
Why not?
Because A still has that backdoor path to the outcome, Y, YAD. The proxies S and Q are related to A, but they don't completely block its influence, especially if they have measurement error.
Okay, so simple conditioning isn't enough? How do proxy controls work then?
It's actually related to IVs, again, in a clever way. You can essentially use one proxy, say Q, to instrument the other proxy, S, or perhaps the treatment D itself, depending on the setup.
Instrumenting a proxy with another proxy.
Yeah, it's a way to deal with the fact that both S and Q are noisy measures of the true underlying A. By using their relationship, you can filter out some of that noise and measurement error to get closer to the true causal effect of D on Y. Zvi Griliches did a lot of work on this back in the 70s.
Zvi Griliches, okay. So back to education one last time. Y is earnings, D is college degree, A is hidden ability. S and Q are two different test scores. How does it identify alpha, the return to college?
By setting up the right statistical moment conditions, using the relationships between Y, D, S, Q, and the observed X, you can actually isolate alpha, the effect of the degree D.
Even without perfectly measuring A?
Even without perfectly measuring A, you typically can't identify the direct effect of A itself on Y using this method, but you can often identify the effect of D. And again, modern methods like DML are used for estimation.
That feels like making really smart use of imperfect information. Is there a good real-world illustration?
The chapter uses a compelling, though perhaps stylized, example. Estimating the effect of mother's smoking, D, on infant birth weight, Y.
Okay, we touched on this. The unobserved confounder A was assumed to be something like income or socioeconomic status.
Exactly. Hard to measure perfectly, likely affects both smoking and birth weight. So they needed proxies.
And the proxies were?
They used mother's education, Q, as one proxy. The idea is education is related to income SES, A, and might influence smoking, D, but plausibly doesn't have a direct biological effect on birth weight, Y itself, only indirectly through A or D.
Okay, that's the proxy treatment control. What was the other one?
Parity, the number of previous pregnancies.
How does that work as a proxy?
The thinking is that family size parity might reflect underlying income, SES, maybe affecting resources available, but parity itself is likely not directly caused by the mother's current smoking decision, D, or her education Q. It acts as a proxy outcome control.
Wow, those are really thoughtful assumptions about the causal structure. What do they find?
Using this proxy control setup, they found, quote, substantial evidence that smoking causally leads to lower infant birth weights. The estimate was around -1.68 ounces per day of smoking.
A clear negative effect, even accounting for the unobserved income confounder via proxies.
Right. It shows the potential power of this approach when you have plausible proxies.
Are there extensions to nonlinear models here too?
Yes, that's a more recent area of research. Generalizing proxy controls to non-parametric settings. It involves more assumptions, of course.
Like what?
Things like assuming the proxies in the confounder are discrete, meaning they take on a limited number of values. And a relevance condition, similar to IVs, ensuring the proxies S and Q have enough joint variation to actually provide leverage.
So you need the proxies to be related enough to A, but different enough from each other.
Something like that. The math gets complex, involving formulas that essentially perform a kind of IV regression using one proxy to instrument the other.
But there's a catch, I assume.
A big one. While you can test the relevance condition with data, the core assumptions about the causal graph, like, does education really have no direct effect on birth weight? Is parity really not caused by smoking? Those are not testable from the data alone.
Some hinges on domain knowledge.
Absolutely. Their validity relies heavily on contextual knowledge about the empirical problem, as the chapter puts it. You really need to understand the situation you're studying.
That's a crucial reminder. These tools are powerful, but they're not magic. They depend on careful assumptions grounded in reality. So we've just taken quite a deep dive into how researchers tackle this pervasive problem of unobserved confounders. We looked at sensitivity analysis to see how robust our findings might be.
Right, putting bounds on the bias.
Then instrumental variables, finding that external Z to create a quasi-experiment.
Leveraging that clean variation.
And finally, proxy controls, cleverly using multiple imperfect measures of the hidden confounder.
Yeah, making the most of the information you do have.
The big takeaway seems to be that hidden variables are a challenge, but not necessarily a dead end.
Definitely not. With the right methods and careful thought about the assumptions, we can still get much closer to understanding true cause and effect, even with messy, real-world observational data.
So as we wrap up, here's something for you, the listener, to think about.
Sure.
Consider a decision you might be facing, maybe at work, maybe personally. Are there potential unobserved confounders at play? Factors influencing both your choices and the outcomes you care about, but that you can't quite pin down or measure.
It happens all the time.
How might thinking about these concepts, sensitivity, instruments, proxies, even just intuitively, help you approach that decision? Could it help you make a more robust choice, or at least help you better understand the uncertainties involved when you know you don't have the full picture? Something to mull over?